Today's lecture is based on chemical analysis. It is a very important area where the aspect of and importance of chemical analysis have been highlighted. Test methods that are used to find out total solids, total dissolved solids and total suspended solids. Now, one would like to understand why is there a necessity, because when we talk about the hardness of water or the water not being pure or water unfit for drinking, it is mostly because it has some dissolved solids and some suspended solids, and what is the total content of these solid needs to be understood. The principle, a well mixed sample is evaporated in a weighed dish and dried to constant weight in an oven at 103 to 105 degrees centigrade. The increase in weight over that of the empty dish represents the total solid. So, it is simple procedure that any sample is just taken and evaporated on a weighed dish. Interferences: highly mineralized water with a significant concentration of calcium, magnesium, chloride and sulphate may be hygroscopic and require prolonged time, proper desiccation and rapid weighing. Exclude large floating particles or submerged agglomerates of non-homogeneous material from the sample if it is determined that their inclusion is not desired in the final result. The limit sample to no more than 200 milligram residue. So, that means that any sample should not have more than 200 milligram of total solids, otherwise that sample requires to be rejected. For total dissolved solids, the principle again is that a well mixed sample is filtered through a standard glass fiber filter and the filtrate is evaporated to dryness in a weighed dish and dried to constant weight at 180 degrees. The increase in dish weight represents the total dissolved solids. Dissolved solids are the ones which we cannot see through our eyes, but they are still in the water and they need to be identified, and that is why the temperature is kept at a higher temperature. For total solids, it was only 103 to 105 degrees, but for the total dissolved solids, the temperature is 180 degrees centigrade. The interferences that are generally to be avoided are highly mineralized water with a considerable amount of calcium, magnesium, chloride and sulphate content may be hygroscopic and require prolonged dryness and proper desiccation and rapid weighing. And here also the residue must not be more than 200 milligram, otherwise the sample needs to be rejected. For total suspended solid, the protocol for testing is that a well mixed sample is filtered through a weighed standard glass fiber filter and the residue retained on the filter is dried to a constant weight at 103 to 105 degrees centigrade. The increase in weight represents the total suspended solids. If the suspended material clogs the filter and prolongs filtration, the difference between the total solid and the total dissolved solid may provide an estimate of the total suspended solids. Here the interferences are: for sample high in dissolved solids, thoroughly washed up filter to ensure removal of dissolved material. Prolonged filtration time resulting from the filter clogging may produce high results owing to increased colloidal material captured on the clogged filter. Here also the limit should be that it should not exceed 200 milligram in the residue. Now, these are different parameters in water which needs to be tested for its purity content. Then the next parameter for the purity content of water is the determination of total hardness in water sample. Total hardness, you must have often heard that this water is soft and this water is hard, and if the water is hard it cannot do a proper washing. What does this term hardness or softness of water actually mean? Total hardness is defined as the sum of the calcium and magnesium both expressed as calcium carbonate in milligram per liter. When hardness numerically is greater than the sum of carbonates and bicarbonates, alkalinity is called carbonate hardness. The amount of hardness in excess is called non-carbonate hardness. The hardness may range from 0 to 100 milligram per liter depending on the source and treatment to which the water has to be subjected. It can also be determined by EDTA titometric method. As calcium carbonate, if it has to be estimated as calcium carbonate, the methodology uses EDTA or ethylene diamine tetraacetic acid and its sodium salt for a chelated soluble complex when added to a solution of certain metal cations. If a small amount of dye such as erychrome black tea or calmagmite is added to an aqueous solution containing calcium and magnesium ions at a pH of 10 plus minus 0.1, the solution becomes wine red. If EDTA is added as a titrant, the calcium and magnesium will be complex and when all of the magnesium and calcium has been complex, the solution turns from wine red to blue, marking the end point of the titration. The interferences that needs to be checked in this case are some metal ions interfere by causing fading or indistinct endpoints or by stoichiometric consumption of EDTA. Reduce these interferences by adding certain inhibitors before titration. Suspended or colloidal also may interfere with the endpoint. Eliminate this interference by evaporating the sample to dryness on a steam bath and heating in a muffle furnace at 550 degrees centigrade until the organic matter is completely oxidized. Dissolve the residue in 20 ml of 0.1 HCl, neutralize to pH 7 with 1 normal NaOH and make up to 50 ml with distilled water. Cool to room temperature and continue according to the general procedure. So, that is how the EDTA is used as in the estimation of hardness, particularly in terms of calcium carbonate. Determination of alkalinity. Alkalinity of water is its acid neutralizing capacity. It is significant in many uses and treatment of natural waters and base water because the alkalinity of many surface water is primarily a function of carbonate, bicarbonate and hydroxide content. It is taken as an indication of the concentration of these constituents. The measured value may also include contributions from borates, phosphates, silicates or other bases if these are present. Raw domestic wastewater has an alkalinity less than or only slightly greater than that of the water supply. Range of alkalinity is 2000 to 4000 milligram calcium carbonate per liter. Determination of chloride. We often say that there is chloride present in water. Now, what does that mean? Chloride in the form of chloride ion is one of the major inorganic anions in water and wastewater. The chloride concentration is higher in wastewater than in raw water because sodium chloride is a common article of diet and passes unchanged through the digestive system. A high chloride content may harm metallic pipes and structures as well as growing plants, and the method for determination is the argentometric method. Oil and grease, how they are determined in water sample, because sometimes water does have some oil particles floating on the top. Oil and grease is defined as any material recovered as soluble substances in the solvent. A known oil is defined as a sample of oil or grease that represents the only material of that type used or manufactured in the processes represented by wastewater. An unknown oil is defined as one for which a representative sample of the oil or grease is not available for preparation of standard. So, sometimes it could be a known oil, that means there is an oil spill where you know that this type of oil was floating on the water, and sometimes it is unknown, but there is a protocol for testing of these oils and grease in water. Method for extraction of banned amines from colored textile articles and dyes. This method describes a procedure to detect the use of azo-colorants banned by the ordinance on commodities in the manufacture and treatment of colored textiles, particularly textiles made of cellulose and protein fibers. The detection of banned azo-colorants in synthetic fibers made of polyester and polyacrylate may require still additional steps. So, there are testing protocols. What I am trying to draw your attention is that these protocols have to be strictly followed. The chemical analysis cannot be done at one's whims and fancy. One has to follow the procedure, and for every banned chemical there is a testing protocol prescribed by the government or the ordinance. Reductive cleavage of azo dyes. 17 ml of citrate buffer, which is at pH 6 solution, preheated to 70 degrees approximately, is added to the reaction vessel and shaken well. It is kept in a water bath with continuous shaking for 30 minutes or so at 70 degrees. 3 ml of freshly prepared sodium dithionite is added and shaken well. Heating in the water bath is continued for 30 minutes approximately with continuous shaking. The reaction vessel is then taken out and cooled to room temperature in about 2 minutes by keeping it in ice cold water, and thus the reduction of the azo dye to amines takes place. Separation and concentration. The liquid-liquid extraction is carried out by using diethyl ether as a solvent. All the extract from the reaction vessel is transferred to the separating funnel. About 10 ml of the diethyl ether is added to the reaction vessel and stirred well. The extract is transferred to separating funnel. This process is done twice more. Now, I will explain you one thing, that extraction is not done just one time. One can take 10 ml or into 3 times, or one can take 30 ml in one time. Now, you will think that why should we do 3 times the same thing when we can do with larger volume in one time, but the partitioning coefficient does not separate itself completely if we do it one time. So, that is why 3 times with lesser volume of solvent is recommended, but not one time with larger volume of the solvent. Method for the extraction of pentachlorophenol. This method is used for the extract of pentachlorophenol or PCP present in textiles, dyes and auxiliary chemicals. Extraction of PCP from textiles, 20 to 30 grams of fabric sample is accurately weighed out and cut into small pieces of about 2 centimeters by 2 centimeters. The sample cutting are transferred to the Soxhlet of the Soxhlet extraction assembly. About 200 ml of methanol is added to the extraction flask. Sufficient quantity required for 1.5 cycle. extraction is carried out for 40 cycles and it takes almost 8 to 10 hours. The extraction is concentrated by distillation in the oxalate itself. The flask is removed. When 5 to 10 ml of extract remains, the flask is then cooled to room temperature and analyzed on GC machine for the content of pentachlorophenol. I would like to tell you at this point of time that pentachlorophenol is used as a preservative, and any amount which is remaining as an excess, as a residue, is injurious. Sulphate analysis. Sulphate is widely distributed in nature and may be presented in natural waters in concentrations ranging from a few to several thousand milligrams per liter. Mine drainage wastes may contribute large amounts of sulphate through the pyrite oxidation. Sodium and magnesium sulphate exert a cathartic action. The tubidimetric method is applicable, which is done by UV vis spectrophotometer. The tubidimetric method is applicable, which is done by UV vis spectrophotometer. How does this procedure take place? Calibration curve is made as per the condition described in the text. Take 20 ml of the sample, add 1 ml of the conditioning agent in each standard solutions and mix in stirring apparatus. While stirring, add a spoonful of barium chloride and begin timing immediately. Stir for 60 seconds at constant speed. After stirring period has ended, pour the solution into absorption cell of the spectrophotometer and measure the absorbance at 420 nanometers after 5 minutes. Same procedure is followed for brine. If sulphate is present, then it would give absorption at peak at 420 nanometers. Phosphate analysis. Again, whether the water is contaminated with phosphate or not can be found out by this analysis. Preparation of standard for calibration curve. Preparation of standard of 0.1 to 0.5 in 100 ml of deionized water is prepared. Addition of 4 ml of molybdate and 0.5 ml of stannous chloride is carried out. After 10 minutes, but before 12 minutes, the solution is measured at 690 nanometers in UV visible spectrophotometer. For sample, again 100 ml of the sample, 1 drop of indicator. If sample turns pink, add acid to discharge the color. Add 4 ml of ammonium molybdate and 0.5 ml of stannous chloride. Wait for 10 minutes, and before it ends 12 minutes, the measurements must be taken on the UV vis spectrophotometer at 690 nanometers. Method for sample preparation for the testing of heavy metal traces. About 0.1 gram of the sample is taken and weighed accurately. About 2 to 5 ml of concentrated nitric acid is taken in a clean conical. The sample is transferred to the beaker and boiled with frequent addition of acid to maintain the levels till the sample is digested. If the digestion of sample is not complete, add about 2 ml of concentrated sulfuric acid and boil until the digestion is complete. If needed be, the process be repeated. After complete evaporation of the acid, add some ultra pure water and filter it in 100 ml standard volumetric flask. The solution is made up of 100 ml with ultra pure water. A blank solution is also prepared in the same manner as specified above, and simultaneously the solutions are analyzed on atomic absorption spectrophotometer or ICP, that is inductively coupled plasma spectrometry. Method for sample preparation for the testing of pesticide. We just had learned that GC is the ideal machine for testing of pesticide. Extraction is a very important step when we are analyzing pesticide. Time and again I have emphasized that extraction plays a very crucial role. Extraction of pesticide from textiles and sample preparation is very important and a little tricky. 20 to 30 grams of the sample is accurately weighed out and cut into small pieces of about 2 centimeters to 2 centimeters. The sample cuttings are transferred to SOC slate and put into the SOC slate extractor assembly. About 200 ml of hexane is added to the extraction flask, and this is sufficient quantity required for 1.5 cycles to run. Extraction is carried out for about 40 cycles, which takes about 8 to 10 hours. The extract is evaporated to dryness at not more than 50 degrees centigrade using rotary vacuum evaporator. Why? Because this is a hexane solvent. In earlier clays, it was methanol solvent. The flask is removed when extract is dried in the flask and it is cooled at room temperature. Sodium sulphate is added and is to remove the water samples that may be present in the sample. During the process of extraction, some water may have come into it. The residue is immediately dissolved in hexane and made up to 5 ml. This is analyzed by GC. If the analysis cannot perform immediately, the sample must be kept in deep freezer, because pesticides are liable to get decomposed at higher room temperature. So, they need to be preserved. Having done the extraction, it is important, if the analysis is not taking place at that particular time or for some reason the analyst is busy, the sample must be preserved carefully. Extraction of pesticide in water or liquid sample, that was from the solid sample, and this particular method is from the liquid samples. About 200 ml of the sample is transferred to the separating funnel. About 100 ml of 15% dichloromethane having 15 ml of DCM and 85 of hexane is added to the separating funnel and stirred well, or rather shaken well. This process is done twice. This process is done once more. The separating funnel is shaken for a few seconds. The pressure is in the reaction vessel is released, keeping the vessel at an angle, and by opening the stopcock. Repeat this process 2 to 3 times. After the formation of 2 layers, the lower layer, which is the aqueous layer, is collected in a small beaker. The upper layer, which is the organic layer, is collected. The aqueous layer is transferred to the separating funnel, and about 70 ml of 15% DCM is again added, and the process is repeated 2 times again. To this, sodium sulphate is added to the organic layer to remove any traces of water molecules. The extract is evaporated to dryness at not more than 50 degrees using rotary vacuum evaporator. The residue is immediately dissolved in hexane and made up to 5 ml, and then it is analyzed on GC or GCMS for its detection. So, you saw that for different banned chemicals, there were different methodologies that were adapted, and yet we have not completed the whole story of analysis. There are different types of analysis, as I said, which are equally important. Now, another aspect to find out determination of total organic carbon and how this method is viewed in the whole scenario is also very, very important for a chemical analyst. So, I thought that I should dedicate a part of the lecture for explaining you what is total organic carbon and how it can be determined. Importance of TOC, we will refer as total organic carbon as TOC. The importance for determination of total organic carbon for solid sample is immense. The methods represent are chemical oxidation, combustion, acid treatment and ashing. The advantages of different methods as well as problems that can be encountered during analysis will all be discussed here. The detection technique used for TOC determination and on the topic of volatile organic carbon, that is the VOC, that deserve particular attention when carrying out the TOC determination, in particular with solid samples. Determination of total organic carbon, that is TOC. Determination of total organic carbon is carried out in different research areas. The data thus obtained are some of parameters and are of interest in different environmental and industrial settings. Examples of TOC analysis include indication of water contamination by synthetic organic compounds. If we want to find out whether a water has any organic contaminant or not, this is the best method to find out. Chemical characterization, degree of humidification of waste, estimation of carbon content of soil, carbon cycle of soil and carbon fluxes in aquatic system. Consequently, carbon has to be determined in solids, soil, sediment, rocks, aquifer material, and in liquids, groundwater, wastewater, sea water, but also in extracts and leaches. Forms of carbon that are present. In general, carbon is present in two forms, inorganic and organic. So, we will refer it as IC and OC respectively. Minerals such as calcite, dolomite are the predominant representatives of IC in soils. Carbonate minerals have a great influence on soil because of their solubilities, their alkalinities and their pH buffering properties. Carbon dioxide, carbonic acid and its dissociation product represent OC in water. Particulate calcite is also present in soil and sediments. Residues of animal, plants or microorganisms in various states of decomposition and elemental carbon like coal, charcoal, graphite are considered to form organic fraction. Charcoal refers to the pyrolyzed residues of terrestrial biomass in the elemental state. OC is present in the organic matter in about 48 to 60% of the total weight. Soil organic matter can be divided into two groups of substances, humic and non-humic. Potable sea and waste waters have a different OM content. Particulate OM extends over several degrees of magnitude ranging. Methods of TOC determination. Methods for TOC determination are presented. Oxidation of OC, that is organic carbon, by means of wet or dry combustion or by chemicals are the most widely used methods. Other methods include application of hydrogen peroxide, manganese at different oxidation state, that is manganese 7 or manganese 3, or inductively coupled plasma, that is ICP, to oxidize the organics, as well as near infrared or visible infrared spectroscopy to estimate the organic content or the organic carbon. TOC measurements is achieved in two methods. TOC measurements is achieved in two methods, either by direct method or indirect method. The idea is to convert all the different forms of carbon into simple form, carbon dioxide, which is easy to measure quantitatively. In the direct method, the organic carbon present in the sample is measured in two ways. The first is to remove the inorganic carbon, that is the IC, by means of acid treatment prior to measuring the OC. The second method does not remove the IC. Instead, chemical oxidation is used to determine the OC directly. In the indirect method, the OC content is obtained by mathematical subtraction of the IC content from the TC content. TC is measured by oxidation of all the carbon present, whereas IC is measured in the purging gas from acid treatment or by decomposition after elimination of organic carbon. The indirect method is not applicable to samples rich in IC and poor in OC, because in such cases the result is derived from the subtraction of the two large numbers. So, obviously, if the inorganic carbon content is very high, the latter method will not be applicable. It is only applicable when they are in equal quantities, or if the organic content is much higher. Then from the total carbon content, the organic carbon is derived by subtracting the inorganic carbon. Chemical oxidation. This method uses different oxidizing solution, digestion times and temperature to oxidize the organic carbon. The recorded methods differ in the strength of oxidant used. Oxidation with chromate. The TOC is measured directly. The oxidation is achieved by a mixture of dichromate and sulfuric acid with or without heat. Heat can be applied to accelerate and complete the reaction. The oxidation is based on the Vaclav-Black method, which is where the rest of the oxidant is detected after reaction with the organic carbon. The Vaclav-Black method is the most widely used to analyze soils, organic sediments and waste, because it is easy and cheap method. Its major limitation is that only the most active OC is oxidized. The quantities of OC recovered depends on soil type and nature of the organic material therein. Organic carbon from the organic fraction called humus, lipids and proteins are probably not completely oxidized. Some authors consider elemental carbon inert to chromate oxidation, whereas others report that various quantities become oxidized. So, there can be a little debate whether the chromate method is the best method or not, but however, it does give good results. So, with this we have come to an end of the analysis of total organic carbon and how the inorganic carbon and the organic carbon can be estimated from these results. Then we switch on to the next topic, which is of equal importance. We have been talking in the past about heavy metal toxicity, how injurious it is to our body, to us, is what we should need to understand first in order to be able to analyze. Where do these metals come from? Heavy metals come from major industries like paper, pulp, mills, paper boards, and metals like chromium, copper, mercury, lead, nickel, zinc come from there. Then building paper, paper boards also add on to metals. Organic chemicals, petrochemicals add on to cadmium, chromium, iron, mercury, lead and tin contamination. Alkalis, chlorine, inorganic chemicals, fertilizers, petroleum refining, basic steel work, foundries. You find that everywhere cadmium, chromium, copper, iron, these are common metals that are contributed from the industries. But there are 9 notorious heavy metals that need to be protected, and that is why so much of emphasis has been given. Arsenic, cadmium, chromium, cobalt, copper, nickel, mercury, lead and zinc. Toxicity of heavy metals. Each one has its own very toxic effect, and I have just highlighted the toxic effect of these metals in this particular lecture. Arsenic, chemically combined arsenic can exist in the +5 oxidation state or +3 oxidation state, of which latter is generally more toxic. A major biochemical effect of arsenic is that it inhibits the production of adenosine triphosphate ATP, a key intermediate in energy yielding metabolic processes. Arsenic also complexes with coenzyme, preventing them from carrying out their function, and is coagulating, is responsible for coagulating proteins. Arsenic disaster. Arsenic contamination of groundwater in Bangladesh is the biggest mass poisoning case the world has ever known. Although arsenic can be detected in trace quantities everywhere. Its abundance in the earth crust is about 1.8 ppm parts per million, making it roughly as abundant as molybdenum or tin. Arsenic's concentration is considerably high in soils and groundwater than in the earth crust because of its accumulation during weathering and translocation in colloid fractions. Then comes the lead poisoning. Lead poisoning is an environmental and public health hazard of global proportions. Children and adults in virtually every regions of the world are being exposed to unsafe levels of lead in the environment. In fact, the exposure to lead from different sources such as paint, gasoline, solder enter through different pathways such as air, food, water, dust and soil. Lead emission from the automobiles in the air is one of the major sources. Lead from lead paint sources deteriorate by breaking or scrapping its invisible pieces as house dust. Now, let me tell you, that is the reason why unleaded petrol has come into existence, because there was so much of lead pollution that was being ejected from these combustion machines. Lead poisoning is a neurotoxin and can lead to poisoning and common pediatric health problems. It has been shown to cause not only neurological disorder, but also causes reproductive problems, diminished intelligence and a host of other illnesses. The major exposure of lead in food is through fruits and grains. Lead in a food chain comes mostly from the air to plants and from livestock eating soils laced with lead as they eat the plants. The ban on leaded gasoline and lead paint have reduced exposure to a large extent, but whatever is existing from the past experiences is still not being evaded completely. Cadmium menace. Cadmium has a number of industrial applications, but it is mostly used in metal plating, pigments, batteries and plastics. Small quantities of cadmium occur naturally in air, water, soil and food. For most people, food is the primary source of cadmium exposure. Since food material tend to take up and retain in cadmium. For example, plants take up cadmium from soil, fish take up cadmium from water and so on. Cadmium has a number of industrial applications, but it is used mostly in metal plating, pigments, batteries and plastics. Small quantities of cadmium occur naturally in air, water, soil and food. For most people, food is the primary source of exposure, and that is why it can go on. Cadmium can get accumulated in the biotic system. Cadmium menace. Cadmium can enter the body through blood by absorption from the stomach or intestine after indigestion of food or water, or by absorption from the lungs after inhalation. However, once the cadmium enters the body, it is very strongly retained. Therefore, even low doses may build up significant cadmium levels in the body. If exposure continues for a long time, cadmium is one of the more toxic of the common heavy metals. Exposure can damage the kidneys and cause a painful bone disease called osteomalacia. Finely divided cadmium oxide particles are particularly dangerous. Inhalation of such dust or fumes can cause pulmonary epithelium necrosis and edema, commonly called as cadmium pneumonitis. Chromium. Chromium 3 is an essential nutrient that can not be toxic unless it is in large doses. The toxicity of chromium compounds depends on the oxidation state of the metal. Occupational exposure to chromium 6 has been associated with increased incidence of lung cancer. The inhalation of chromium compounds has been associated with the development of cancer in workers in the chromate industry. The relative risk for developing lung cancer has been calculated to be as much as 30 times that of controls. There is also evidence for an increased risk of developing nasal, pharyngeal and gastrointestinal carcinomas. The efficacy of chelation therapy in chromium poisoning has also been proven. Hexavalent chromium absorption. Chromium 6 is about 4 times readily absorbed in the stomach as compared to chromium 3. Estimated efficiency is 0.5 to 2%. It is distributed in the cells and they take up chromium 6 via facilitating diffusion through non-specific ionic channels, and the mode of action as the body reduces chromium 6 to chromium 3, the intermediate chromium 5 and 4 states generated free radical and bind to cellular constituents. So, this is the kind of mechanism where the toxicity and its effect of hexavalent chromium can be understood. Coming to zinc, which is another heavy metal, toxic and notorious. Although one of the less toxic metal, zinc has caused some problems when dispersed to the environment. Zinc is not known to be toxic until it reaches levels of 500 milligram. Then it can cause drowsiness, vomiting, copper deficiency. Some of the zinc compounds can be hazardous. These include zinc chloride, zinc sulfate, zinc sulfide, zinc chromates and zinc oxide. Zinc oxide has been identified as the main cause of metal fume fever, also called as brass founders arc or zinc shakes, in an industrial hazard caused by inhaling zinc oxide fumes. It results in neurological damage. Among its symptoms are headache, fever, chills, muscle aches and vomiting. Copper intake. Copper is an essential metal in a number of enzymes. Excessive intake of copper results in its accumulating in the liver. Generally, copper toxicity is increased by low molybdenum, zinc and sulfate intake. Chronic copper poisoning of sheep in Australia revealed that copper retention depended upon the inorganic sulfate status of the diet and the animal. Copper toxicity or deficiency in animal is not merely dependent on copper intake, but also on its dietary level of zinc, iron and calcium. Mercury is yet another but very highly toxic element that is found both naturally as an introduced contaminant in the environment. Although its potential for toxicity is highly contaminated areas such as Minamata Bay in Japan, and in 1950s and in 1960s it is well documented that research has shown that mercury can be a threat to the health of the people and wildlife in many environments that are not obviously polluted. The risk is determined by the likelihood of exposure, the form of mercury present. Some forms are more toxic than the other, as what we saw in the case of chromium as well. Chromium 3 is very less toxic as compared to chromium 6. Similarly, mercury also exists in various forms and some of the forms are more toxic than the others. And the geochemical and ecological factors that influence how mercury moves and changes form in the environment is also very well understood. So, from one form to the other form, the mercury somehow reaches the biotic system and the food chain, and that is how it reaches to human beings. Ill effects of mercury. The toxic effects of mercury depends on its chemical form and the route of exposure. Methyl mercury, that is CH3Hg, is the most toxic form. It affects the immune system, alters genetic and enzyme system and damages the nervous system. including coordination and the senses of touch, taste and sight. Methyl mercury is particularly damaging to developing embryos, which are 5 to 10 times more sensitive than adults. So, for fetus it is highly dangerous. Exposure to methyl mercury is usually by ingestion, and it is absorbed more readily and excreted more slowly than other forms of mercury. Elemental mercury, that is Hg, in the zero oxidation state, the foam released from broken thermometers causes tremors, gingivitis and excitability when vapors are inhaled over a long period of time. Although it is less toxic than methyl mercury, elemental mercury may be found in higher concentrations in environment such as gold mine sites, where it has been used to extract gold. If elemental mercury is ingested, it is absorbed relatively slowly and may pass through the digestive system without causing much damage. Ingestion of other common forms of mercury, such as salts like mercury chloride, which damages the gastrointestinal tract and causes kidney failure, is likely from the environmental source. So, you see that how dangerous and how toxic these metals are, when particularly these 9 metals that I mentioned, and that is why it is important to understand what are the poisoning effect, what is the chemistry behind their reactivity towards the biological system and the human system, and how they should be analyzed and prevented, so that they do not spread over in the environment and do not reach the human. Similarly, cobalt is also one of the 9 culprits of the heavy metal series. Cobalt is essential in trace amounts for human life. It is a part of vitamin B12 and plays a key role in the body's synthesis of this essential vitamin. Cobalt has also been used as a treatment for anemia, because it causes red blood cells to be produced. The toxicity of cobalt is quite low compared to many other metals that I mentioned a while ago in soil. Exposure to very high levels of cobalt can cause health effects. Effects on the lung, including asthma, pneumonia and wheezing, have been found in workers who breathed very high levels of cobalt in the air. Cobalt in the environment. How much of cobalt is present in the environment? Cobalt is a natural earth element present in trace amounts in soil, plants and in our diets. It usually occurs in association with other metals such as copper, nickel, manganese and arsenic crops. Coming to yet another next metal is nickel. It is also not very toxic, but still any overdose of nickel can be in the toxic limit. Nickel is a metal found in the earth's crust. The average worldwide concentration in soil is 8 parts per million ppm. In Ontario, that is Canada, the background concentration of nickel can be as high as 43 ppm, with an occasional area that naturally contains higher concentrations. The amount of nickel contamination in Port Colborne ranges up to 17,000 ppm. So, there it reaches the toxic limit. Nickel toxicity in human: about 10% of women and 2% of men in the population are highly sensitive to nickel. A portion of these sensitive people can develop a skin rash called nickel dermatitis if they are exposed to nickel through direct contact. This is most common type of reaction to nickel exposure. With nickel toxicity, the type of nickel speciation is very important. Its form of either in the form of metallic form or oxide form or any other form, and the ease with which it dissolves in water affects the toxicity and the consequences to human health. The most serious health effect occurs when nickel is inhaled. Increased risk of respiratory cancer due to chronic inhalation of fumes or fine particles when exposed is to be known as carcinogenic form of nickel oxide. Asthma, nasal and sinus problems are usual symptoms that nickel can cause. So, you have seen that out of these 9 metals, not all were very dangerous, but however, they are equally dangerous when they are in very high quantities, and at the same time they need to be analyzed properly, so that they can be extracted from the matrix and the level of contamination or pollution can be estimated correctly.